What's going on? Oh, it came out. Okay. So I guess almost everybody's back. So I'm going to start on part 2, which is on arches. So in part 1, I talked about the UCF and some of the, essential concepts for following what goes on in these UCF components. And so now I'm going to talk about this particular UCF component, arches. Okay, so if you want to follow along or just look at the code or anything like that, then the actual location in the tree is in the source, CCA, components, arches. So I'll write that up here. Okay, so what is arches? So arches is a component in the UCF framework that's designed for finite volume LES calculations. So it's a fluid dynamics code, CFD code, it's a finite volume code, and it's using LES. So it's using an explicit time integrator. So we talked about how the UCF is designed for these time-dependent PDEs. So this is using an explicit time integrator. It uses tabulated chemistry. So it doesn't do all the chemistry in line. It doesn't do any kinetic calculations during the solution. It just uses a table where all those reactions are tabulated. And it also uses a pressure projection method. And if you use the UCF to do this in to do these massively parallel simulations, you can get simulations that look like this, where you get these large-scale structures. So using this UCF to parallelize, you can get a lot of computational time, and you can get these really interesting, novel simulations where you're resolving a lot of the length scales of the flow. Okay, so I guess what I'm trying to say is this is a really unique tool. And part of the reason it's so unique is because it's built on top of the Uinta framework. So I'll talk a little bit about its capabilities. There's a couple of subgrid models available. There's a Smagorinsky model, an incompressible dynamic model, a compressible dynamic model, a local dynamic model. So there's all these options for subgrid turbulence models. And those are the corresponding files where they're located. And all those are child classes of a turbulence model class. Okay. I also want to talk a little bit about combustion chemistry and how Arches does combustion chemistry. So combustion chemistry is extremely, extremely expensive. It can take an otherwise tractable computation and make it completely impossible to do. So what am I talking about? Okay. So if I have a reaction rate, maybe this is just a simple, very simple reaction rate. Just say, for example, we have first order with respect to A, second order with respect to B. So these reaction rate terms are showing up in our transport equations. We have partial with respect to T of our concentrations. We're going to have some stuff, and then we're going to have a reaction rate source term. Okay. So does everybody follow what I'm talking about here when I'm writing these reaction rates and writing these kinetic expressions? Okay, I'll assume non-response means yes. So okay, what's the big deal? We just solve it, right? Really easy to solve. Well, not really. So these K's, yeah. So there's a lot of species and there's a lot of Ks, and when you're dealing with combustion that's happening on all these different tiny little scales, and you've got to do that at every single cell, and you've got like 1,000,000 grid cells, and you've got 300 reactions for a really simple combustion of like methane. I mean, methane combustion has something like 100 species and 300 reactions. So you have to take 300 of those reaction rates. So this is reaction rate of A for one reaction. So now if you have 300 reactions, now you've got 300 rate constants. You've got to track these 100 species. You've got to track 100 different species using 100 different transport equations. So it's just a really, really bad idea to try and do chemistry directly because it can quickly become out of hand. And for parallel computations like this, they'll grow astronomical. Okay, so what ArchES does is it uses tables. It uses a chemistry preprocessor, or sort of you can think of it like a preprocessor. So this is the Cantera software I mentioned last week, and it uses so we just use a piece of software, in this case tabprops, which runs Cantera and generates tables. So it tabulates all the different possible species concentrations. So I'll just talk about that process a little bit because it's not as straightforward as it sounds. So we're using two concepts, reaction models and mixing models. So reaction models, what we're saying is we have a huge set of species and temperature and density and viscosity and all these different characteristics of a state. So I've denoted that with phi. That's the thermochemical state of our simulation. And each different cell is going to have a different phi. You can think of phi as a value that's going to be unique to an infinitesimal point in any sort of combustion system. So we have a whole lot of phis, and phi has a whole lot of variables. And this is part of the reason why combustion is so difficult. We have a whole bunch of different species and variables and things, and those variables are changing at every single point in time. So the idea is we can make an assumption that all of those, that huge set of thermochemical variables, like all the species, the temperature, viscosity, all that stuff, we can make an assumption that all of that can be characterized using a smaller set of parameters that I've called eta. So we can use something like some variables like mixture fraction. Mixture fraction describes the fuel to air ratio. It's 0 if it's completely fuel and 1 if it's completely air. Or sorry, 0 if it's completely air, 1 if it's completely fuel. We can use H, which is some enthalpy-related variable. We can use sigma Cassi, which describes the statistical distribution of our mixture fraction. So we can use this reduced set of parameters, and then based on those reduced set of parameters, we can assume that there's one single thermochemical state described by those the particular values of eta. So in other words, we create a map from eta to phi. In this way, we only have to track, 1 or 2 or 3 variables, and we can back out 100 variables, or however many variables we want. Okay, so this saves a huge amount of computational time. And the idea is the error involved with doing that is marginal. Okay? But now we have this added complication that we're not looking at infinitesimal grid points. Okay? So This works fine if we're looking at an infinitesimal grid point, but we're not. We're looking at LES. So in LES, we have some cell. Maybe there's some fuel here. Maybe there's some fuel here. Maybe oxidizer here. Maybe some pockets of fuel here. If this is the size of our grid. What we're doing with LES is we're saying, we're just going to treat that as homogeneous. But it's not homogeneous. So there's not a single eta here. There's an eta here, eta 1 here, eta 2 here, eta 3 here. You get the idea. There's a whole bunch of different etas in a single LES grid cell. So we can't just say, okay, here's our one eta, and there's our one phi. So this mapping doesn't work for LES. So with LES, we can't just plug in a reaction model. So what we do is we use mixing models. So a mixing model says, we have some PDF for mixture fraction, PDF for heat loss, PDF for any kind of eta variable, any of these eta variables. So we have some distribution. Maybe it looks like that. Who knows? Who knows? We don't want to assume anything about what it looks like. That's a whole different topic. So we have some PDF for our eta variables, and so what we can do is integrate over those PDFs. So instead of mapping a single eta to a single phi, now we map a whole bunch of different possible values of eta to a whole bunch of different possible values of phi. And then we integrate over our PDF. And what that does is it gives us a single filtered value of phi. Because ultimately that's what we want in our large eddy simulation calculation. We want a filtered value of phi because we're solving for filtered quantities in LES. Okay. So I'm just going to kind of let that sink in. Does that make sense to everyone? Should I say it again in a different way? Should I? Okay, so maybe another way to say that is, at each of these different points, we also have a different phi. And so what we're trying to do is, instead of picking one value and saying, okay, we'll just use that value, that's not going to be very good. Because if we happen to pick the wrong spot in that cell, then we're going to get completely wrong values for phi. So the idea is to weight all the different phis by their different probabilities. So if the probability of this, the probability of this state is pretty low, so that phi is not going to be very likely. But the probability of this state is really high, so that phi is going to be weighted higher. And so when you average over all these different possible values of eta, then you get an average of all these different possible values of phi, and that's basically what LES is tracking, are these averaged values. So we're getting phi filtered quantity. And this is basically just a spatial average, or some sort of average. Okay? So this is how ARCHES tracks chemistry. So rather than trying to solve, 300 coupled, differential equations for all these different concentrations and rate constants and all that, instead what it does is it does all of that offline, and it does all of this integration over PDFs offline. And then what happens online is we're tracking this reduced set of ADA, filtered ADAs. So we feed those into the table, and out of, so we feed these into the table, and then out pops feed filtered. Okay. And the way we know what this PDF is we put some variables in ADA that happen to describe that PDF. So we might put the variance, just say. Or if we're presuming a PDF shape, we might have other factors like alpha or beta. And all these different variables that we're tracking are going to tell us something about this PDF, so that we know where in the table to look. And then when we look in that spot in the table, we get this filtered feed that we're looking for. Okay? Does that make sense to everybody? I think I put everyone to sleep. Okay, so that's combustion chemistry in Arches. Just a little bit more about the capabilities, and then I'll move on to something different. So we've also been, this is a more recent endeavor, we've been working on adding DQMOM to Arches. So DQMOM is for multi-phase applications. So we're applying Arches to coal combustion and gasification, and so this requires adding models for two-phase drag and two-phase heat transfer and two-phase reactions and all these different coal-related models. And in parallel with that, there's also been this development of a new transport equation framework. So this is a lot nicer than what's currently implemented in Arches. The transport equations in Arches are all hard-coded, kind of cryptic, and if there's a bug in there, there probably are a couple hidden in there somewhere, but who knows. So this transport equation framework is a lot more transparent. It's very easy for the user to add transport equations, as many as they want, through the input file. These transport equations are handled in a flexible manner, and each of these transport equations can have their own discretization schemes. So you could use super B for one and upwind for another, or if you wanted a high order method, you could code a high order method. You can use different time integrators. You can use first order, second order, third order. And this is all extensible. So if you wanted to add your own time integrator, maybe an Adams-Bashforth method, you can do that. If you wanted to add, an eighth order Runge-Kutta for whatever reason, you can do that. It's totally up to you. And one of the really nice things about this too is you can create source terms and add them to different transport equations in your input file. So you can kind of network all these different things together. And you can do it all from the input file. Okay? So now I want to talk about how all of this stuff fits together. So when we looked at the Poisson example, we saw that there were two really important methods. And one was schedule time advance and one was time advance. And so as part of this CCA, this common component architecture, each component has to define a way to advance the simulation in time. So Arches is also going to have a schedule time advance and a time advance. If you look at any other component, they're going to have a schedule time advance and a time advance method. So there's a lot of parallels between the Poisson component and Arches. Even though the Poisson component was really simple, there's still a lot of parallels there. Okay, so this is kind of a generic representation of what's going on. So at the very top is the Arches component. So this is the point where we interface with the framework and you went to take stuff over. So I'm going to ignore that for now. So the next So arches calls the framework calls this arches time advance method. And so what that does is it tells arches, okay, time to advance the solution in time. So what arches does is it calls the nonlinear solver. The nonlinear solver is the workhorse. That's where all of the actual algorithm happens. So there's this method in the nonlinear solver called nonlinear solve. Okay. So this nonlinear solve method goes through and it's got a list of things it needs to do, and that's part of the LES algorithm. And so it has connections to all of these different things. So there's things for a mixture fraction transport equation, an enthalpy transport equation, momentum transport equations, which are kind of what you'd expect. There's also pressure solvers, radiation solvers, boundary conditions, transport equations, DQ-MOM stuff, the chemistry table stuff, pretty much everything. And everything's handled by this nonlinear solver. And so it knows how to call this class to tell it to update the mixture fraction equation. It knows how to call the boundary conditions to apply the boundary conditions. And not only that, but it knows it's got a particular order that those things happen in. Okay. So at this point, I'm going to kind of break away from the code side and look at the algorithm. So are there any code-related questions before I change gears? Okay. Okay, so I'll talk about the algorithm. Details aren't that important, but basically this is just a pseudocode algorithm for what Arches is doing. And this is stuff like solving for the, updating the scalar equations, solving for, guessing the density, updating momentum transport equations, and so on. And there's also this spot where the table lookup happens and where the DQ-MOM stuff is solved. There's stuff for computing the velocity without doing the pressure projection. Here's where the pressure projection is done, and then we update the projected velocities. So all of this stuff is happening in the nonlinear solver class. So all of these different tasks are just tasks happening in the nonlinear solver. Okay. All right. So questions about the Arches algorithm? I'm not going into too much detail about the algorithm, but I think you kind of get the idea.
You said it's working with finite value method?
Yes.
And which algorithm? I mean, simple.
It's using simple.
Simple.
Yeah. Okay, well.
And it works for both compressible and incompressible.
Yes. Yeah. So this is primarily in compressible code, because with combustion, the reactions and the heat transfer are always changing the density, and so it's really important to have a compressible formulation. So, yeah.
Compressible flow? I mean, so you say it accounts for shocks too? Or is it a compressible component of density?
Low Mach number compressible flow.
Okay. So that's
Interesting point.
Yeah, people don't say compressible.
okay.
Okay, well, that's all I had. So just to summarize, we went over the Uinta framework and saw how how a component. So we looked at an example component, the Poisson component. Saw how a component works, how the framework works. Talked a little bit about Arches and how it's sort of structured. And if you dive into Arches, then you can use a lot of these examples as sort of guides to what it's doing. What does that call mean, or what does this call mean, and or how do you request something from a data warehouse? These examples are really useful for doing that. And that's it. So thanks.
Thank you.
I don't know so many people who are interested in watches.